lecture here. So, again, 3.1. And the problem is, I'm going to draw a picture here. I've got a function, f of x. I've got a certain point called x, and I go up there and I find the corresponding y value is called f of x. You guys okay with that? Yeah. I mean, the whole function is called f of x, but at this certain x, that y value is f of x. And what I'm trying to do is find the equation of this tangent line. I'm trying to find, well, I can start by finding the slope of this tangent line. I wish I could find the slope of this tangent line. And then, I've previewed this thought. The thought is, well, wait a minute. If you're going to find the slope of a line, you really kind of need 2 points. You know, we've never really done it with 1 point. That's kind of the whole problem. How am I going to get a slope at 1 point? So the game we play is this. Here's the game, and I haven't officially presented it like this, but here it is. I want to go ahead and get 2 points. So I'm going to add this little chunk of something. I'm going to call it a change in x. I'm going to add it to this x. So what's this new point over here? X plus delta x. Is that okay? And if I plug it in the function, then I have my second point. And it has a y value. If I go over here, what's its y value? F of x plus delta x. Is that okay with you? If that's the x value, plug it in the function. That's the name of the y value. And then you can calculate, and now you have 2 points. See, we're just doing this abstractly for any old function f. So now you have 2 points, and you can calculate the slope of that line. And is the slope of that line going to be the same as the slope of your tangent line? No. No. Thank you. No. It's not the same. You know, in my picture, it's actually not that far off, maybe. Maybe it's not that far off. And as a matter of fact, what would make it a better approximation of the slope of the tangent line? What do you think would make it closer approximation to the slope of the tangent line? Thank you. If that delta x was a little smaller, if this point was a little closer, or the delta x was a little smaller, I mean, if this point got closer, then you could have this line. That's still a line between 2 points. It's still not really your tangent line, but it's closer. So the blue line is touching at 1 point, and it is the tangent line, and that's what I'm looking for, or the slope of the tangent line. Listen, the book uses this language, and I probably won't ever use this language much again, but they call this line between 2 points, they call it the secant line. Now, when you read this, it implies that there's a lot of trig going on here, and to tell you the truth, there's not any trig going on here. The word secant, in this case, comes from the Greek word to cut. So you're cutting the line in 2 places, I guess. I read that in the book. So I don't know, it is not about the secant trig function. It's really not. So don't get freaked out about that. That's not what it is. Anyway, so it's sort of a different use of the word secant. There might be some connection that I'm not aware of, and then the tangent line, I don't know, it's not really about the tangent function. It's about being tangent to the curve, you know, touching at 1 point. You know what I mean? So I don't have to think of my old trig functions here, even though I'm using that language. The secant line is the one that cuts it in 2 places. The tangent line is the one that touches at 1 place. If I want the slope of the secant line, that's kind of how they start. They say the slope of the secant line, and they say that according to this picture, it's that f of x plus delta x minus f of x all over delta x. That's it. And that's old. That's not the new calculus idea. The new calculus idea is I want the slope of the tangent line, and I've already sort of previewed this. How do I make this the slope of the tangent line? And I just sort of talked you through it. I need this I need these 2 points to get closer and closer together, or what? What were you about to say?
I was saying, x plus delta x.
Well, I need him to move closer. Another way to say that is I need delta x to go to 0. I need delta x to go to 0, and then that will make this closer. And then I'll get the slope of the tangent line. You guys following me?
Yeah.
The picture is beautiful. You got a slope between 2 points. If you move these points closer or let delta x go to 0, you end up with the slope at 1 point. So what makes it the slope of the tangent line then is this subtle little thing here. All of a sudden, it's not subtle, it's super. You add this to it. The limit as delta x goes to 0 of this. I mean, now it's calculus. I mean, that was algebra, I guess. Now it's calculus because it contains this limit. And it's the slope of the tangent line. And it's powerful it's the difference quotient with this limit on it. I mean, so I guess we used to refer to this as the old difference quotient. With this limit on it, it's the difference quotient with this. Here's what this is. It's the derivative of the function. And we denote it like this. F prime of x. That's a little prime. And it is the derivative of the function x. The derivative of f of x. And what the hell's the derivative? Let's just say it another way. I can say it 6 ways here. It's the slope of the tangent line. It's the slope of the tangent line. That's what the derivative is. It's the slope of the tangent line to the function I'm going to just add a couple phrases here. To the function f of x at any point x. So the picture kind of shows you that. I just took you through the argument there. I wrote the math down that makes sense. I added this to make it a tangent line. And this is the big, super big idea of calculus. One of the super big ideas in calculus is this. Again, it's about the 3rd or 4th time you've seen it now, kind of. Maybe it's anticlimactic. But we can find the slope of these functions at a certain point. And the rest of chapter 3 is kind of about that. And you got to do this. You got to do this to get this derivative. Any questions? I mean, I took you through the presentation of where this comes from. Now, let's do a problem. I mean, presentation is over. You can read the book. You can look at. I don't know. There's no other way to explain it, really. Let's try a problem. On your quiz Friday, you were supposed to do it for a problem kind of like this. I'll just make one up here. 2x squared minus 5x plus 8. And I want, well, let's just say, I mean, on this test Friday, I might just say, please find the derivative. Find the derivative of f of x, or the derivative.
That was on the quiz, you said?
This was on the quiz. Well, on the quiz, the quiz said, here's a function, do this. That's what the quiz said last Friday. Here's a function, it was a quadratic function. I made up a new quadratic function. But you had a quadratic function, and it said, do this limit. So you were just doing limits, I guess. You weren't thinking about the big picture of what it means and what it is, but this is a super famous limit, and here's what it means, and it's very important. And so that's what I want to do. This question now says, please find the derivative, and the derivative means let's do this limit. So I'm doing the limit, so I'm going to call this f prime of x, and it's the limit as delta x goes to 0 of f of x plus delta x. It's this. Now listen, I'm gonna go ahead and do this. What is f of x plus delta x? Well, I got to take x plus delta x and plug it in my function. So I got to take x plus delta x and plug it in my function. Listen, some of you had struggled with this question, so this is worth going over here. You also have to plug it in there.
I remember it now.
You also have to plug it in there. You plug it in everywhere, there's an x, plus 8. So what did I just do? I just did this. Stick x plus delta x in the function. Minus the function itself. Okay, minus the function itself. 2x squared minus 5x plus 8. Again, the parentheses, I'm going to subtract all that. I'm going to change the signs and add, or I'm going to subtract all that, all over delta x. So when you finish this problem, it takes some work. It takes some foiling and cleaning and foiling. It takes some algebraic work. But when you finish this, you'll have a new function. What will your new function be? When you're all finished with this, you'll have a new function. What will it be?
The slope of the tangent line?
It'll be the derivative of that function. It'll be the slope of the tangent line of that function. It'll be a little formula for the slope of the tangent line of that function. It's this hell of a process, but in the end, you get this cool little formula. You get this new function, which is like a cool little formula for the slope of that function. You with me? I mean, that's what it is. I'm going to say it thousands of times probably, but now we got to do it. And this is where, again, some of you just struggled with your algebra skills a little bit here doing this. So first of all, okay. Right, so now it's algebra, right. I think I'll get rid of my picture.
We got to follow x plus delta x.
Yeah, so first of all, the delta x is like a different variable than the x. And so don't get that confused. And so some students like to say, well, can instead of writing delta x, can I write the letter h? Because it's a different variable, and maybe in some pre-calculus classes they used h instead of delta x, so they're comfortable. I mean, anyway, that's okay. I don't really need to do that myself, but you can do that if you want. The point is, the reason I bring it up is because it is a different variable than x. It's its own thing called delta x.
And delta x will change.
Well, I don't really care what it means anymore. Now it was a change in x. I had it on my picture. I had a picture of what delta x is and what it means. It's a change in x. We're going to let that change in x get smaller and go to 0. But at this moment, I just treat it like a variable, like its own variable, like h or y or something, and I do this algebra. And so here I go. First off, I need to FOIL that out, and it's an x plus delta x times an x plus delta x. It requires FOILing. It's x squared. It's an x times delta x. It's another x times delta x, and then it's a delta x squared. Now, you guys okay with that?
Yeah.
I just quickly FOILed it out. And the middle term is the two of those guys. It's one of them plus another one of them, so there's two of them. So it's x squared plus 2x delta x plus that delta x squared. Now that's just FOILing a binomial, but right, you need that if you're going to be a calculus student. You need to be able to FOIL a binomial. Then I think I need to multiply by 2. Some students multiplied the 2 a little too early. That's bad. You got to do it. You got to FOIL it, then multiply by the 2. I'm going to do that now. I'll have 2x squared. I think I'll have 4x delta x and 2 delta x squared. So you with me? FOIL it out, multiply by 2. That's not very hard algebra, but you gotta do it. I'm going to distribute the -5, -5x, -5 delta x, a plus 8. I'm going to go off the video here. You know what? I don't care. -2x squared plus 5x minus 8. Whoever is on that video should be able to follow that. All over delta x. And now a lot of stuff cancels. So it's just, you got to fight through this algebra without making any mistakes, then it works beautifully. The 2x squared cancels with the -2x squared. The -5x cancels with the positive 5x. The positive 8 and the -8 cancel. And what you're left with, notice this, it's these 3 terms, here they are, it's these 3 terms, they all have a delta x in common. If I factor out the delta x, I'm left with 4x plus 2 delta x minus 5. I just factored out that delta x. It's all over this delta x. You guys with me? A lot of things canceled. Whatever was left had a delta x. I pulled it out. It now cancels. And I'm left with that. Now some of you left that as your answer. You know what you forgot to do?
Put in the 0.
The limit, right. Right. So you do all that beautiful algebra. That is your answer, except, wait a minute, you're doing a limit as delta x goes to 0. And now you can let delta x go to 0, which means this whole term goes to 0, and then the final answer is 4x minus 5. And again, it's not that hard, but it's a I don't know, it's a nice medium calculus problem. This is kind of how calculus starts, doing these limits. I mean, we studied all kinds of funny limits, but this is the important limit that leads you to the slope of the tangent line.
I didn't add the 2x delta x to the 4 delta x.
Right.
I realized I got that wrong.
Maybe. Yeah, maybe.
Yeah, that was on the
Is there any questions about the algebra or the... So I gave you a function and said find the derivative. I guess your job for Friday morning, for Friday, might be to know what the hell that derivative means. And it means do one of these big fancy limits. And you can do it to that you can do it to all kinds of functions. You can do it to all kinds of different kinds of functions. You can do this to any function. And that's the answer. Any questions? So here's a good part B to this problem would be this. So watch this. Here was our function. I'm just going to kind of organize this again. Here was our function. What was the derivative? What's the derivative? Let's
4x subtract 5.
4x minus 5, right. The truth is, now I don't think I'll get to it this week, but we're learning how to do a derivative sort of the long, hard way, actually.
Right.
There's shortcuts to doing these derivatives. Do you guys know about those shortcuts? Well, some people do. Some people maybe have had a little calculus, or they've previewed some calculus, or some people know some stuff. The truth is, there's shortcuts that we'll get starting after Friday. We can do some of these derivatives the easy way. I would call this the hard way, right? The long way. And we'll come up with some shortcuts to do it the easy way. But next week. If you happen to know the shortcuts, don't use them on this test. I mean, you got to do what I ask, which is no shortcuts, long, hard way. Anyway, there's the function. There's its derivative. What is this derivative? What is this derivative?
The tangent, the slope of the tangent.
It's the slope of the tangent line. It's not the tangent line. Some people like to say, oh, it's the tangent line. No. It's a little formula. It's the slope of the tangent line only. The slope of the tangent line only. So if I want, here's a good question. This is a classic. Find the equation of the tangent line at x equals 3. So I want the equation of the tangent line at x equals 3 for this function. Okay, I want the equation of the tangent line. Hold on. The equation of a line. You know about the equation of a line. Feels like, to me, I've been trained where if you want the equation of a line, you need a slope and a point. I need a slope and a point. The derivative is my slope formula. You know, if I plug 3 into that derivative, f prime of 3. Plugging 3 into the derivative. What is the answer?
7.
12 minus 5, it's 7. And what is that 7?
That's your y. And then
That's your back.
Wait a minute now, wait a minute. I
No,
plugged
that's
3 into the derivative.
That's your
The
slope.
derivative is the slope.
That's your slope.
The derivative is a formula for the slope of the tangent line.
7. Oh, so it's 7x. Y.
Well, hold on. So when I plug the 3 into the derivative, that's me finding the slope at this point, right? I'm using the derivative to find this, so this is the slope. Hey, what did I say I needed for a tangent line or for any line? I need a slope and a point.
Yeah.
Well, I got an x value. They didn't give me a y value. How do you get a y value?
Plug it in F of X.
Oh, don't you always get a y value by just, I mean, go to your original function, plug in an x, and you get a y?
Right.
Right. That'll be your point, right? So plugging x into the function gives you your y value. That gives you your point. Plugging x into the derivative gives you your slope. Right? So I will. I need to plug x. Yeah, I need to. What's f of 3? I need to plug 3 in the original function. I think I get 11.
Now we use our point slope.
That's my slope. This is a point. I got a slope. I got a point. 3, 11. I'm ready to write the equation of the tangent line. I do this point slope formula. Y minus the 11 equals the slope times x minus 3. Are you guys okay? That's y minus 11 equals 7x minus 21. I'll add 11 to that side. My answer's down low here. My answer is negative 10. Is that my answer?
Yeah.
Cool.
And that's your.
No,
That's your.
equation of the tangent line.
Gotcha.
Oh yeah, what is that? That's the answer. What is that? That's the answer. It is the equation of a line. It is the equation of the tangent line to that function at that point. I mean, what's cool also is, here's another part to this question. Please illustrate all this for me.
Draw a graph.
Right, that's what I mean. Right, please illustrate all this for me. And what I mean is, maybe let's draw a graph of this function. You guys got a graphing calculator? Can you help me? Type in that function, 2x squared. I mean, I could go find the vertex. I could go, I just want a quick graph of that thing.
Okay.
Oh, I'm thinking it's something like this.
2x squared minus 5.
It's over here, something like this. It has a y-intercept of 8. I know that. It has a y-intercept of 8. Is it sitting over here like this? Is that what it is?
Other side.
Really? The other side.
Oh. My window's too.
Kind of steep like this, kind of skinny and steep. Is it like this?
It doesn't cross that.
It doesn't cry. No, it's up higher.
Yeah, something like that.
Something like that, huh?
Yep.
All right, thank you. That's a picture of the function.
Okay.
Just got somebody help me quick. Just rough and quick. Listen. When x equals 3, where are you when x equals 3? Where are you on the function when x equals 3?
7.
No.
11.
Oh, 11.
11. Thank you. Yeah, you gotta watch out. These two guys, people screw this up all the time. Right. There's an actual y value here on the function. There's another thing here called the slope. Right. Good. Anyway, where am I when x is 3? I'm at 11, I guess. When x is 3, I think that's over here. I'm at 11. You okay with me?
Yeah.
Hey, by the way, does it look like the graph is pretty steep right there? Say yes.
Yeah.
Good. It looks like it's pretty steep. I think it would have a pretty large slope, maybe right there. I mean, I don't know if you think 7 is large. 7, that's kind of a steep slope. Up 7 over 1, up 7 over 1. So that's a pretty steep slope. If I drew the tangent line, you know what's cool? On your graphing calculator, you guys type this in. If you go type in this, what you'll see is a tangent line. You'll see it. You'll see this tangent line. It'll touch right there. you can type in your tangent line, you can type in your function, and just watch them touch each other. Well, excuse me, but it's kind of cool. They just touch each other one time. That's it. That's it. What do I have here? I got a line with a slope of 7. It's got a y-intercept of -10, right? If I know all about algebra. It's got a y-intercept of -10. Apparently that's way down here. But it's got a slope of 7. It's a fairly steep line, and it's tangent right there. It's touching the graph at that point. See, when you do this derivative, in general, again, what you create is a formula for the slope of the tangent line, a formula for the slope of the tangent line at any point. So I can sit there and play this fun game. Hey, what's the slope when x is 0? What's the slope when x is 0?
-5.
-5. What's the slope when x is 1? -1, I guess. I mean, are you with me? I got a cool formula here. I can find the slope at any point I want. The slope at 0 was -5. I wonder what the slope is at 5/4. Right here at 5/4. What do you think the slope is? What do you think the slope of the tangent line is right there?
0 maybe?
0. Well,
According to my picture, right, hold on. If you are at 5/4, let's plug in a 5/4. What happens when you plug in a 5/4? You get 0, don't you? So you have a slope of 0. That's that place right there. That's that place. That's that tangent line, has a slope of 0. That's good. So, in a way, there's some kind of cool, grandiose ideas about the equation of a tangent line, about the derivative. There's some new notation. There's a lot of new stuff in 3.1, but in a way, it's this limit over and over and over again is what it, I mean, this is the derivative. And you can do this to any function. I mean, you can do this to this function. You could do it to a quadratic function like I did. It's fun to do it to quadratic functions. You could do it to a cubic function, but that's kind of a pain because then you got to cube everything out. You could do it to a fractional function. We did this. This was in our homework. We did it with a fraction like this. That was kind of a pain. I guess you could do it with a square root. You know, some kind of a square root. That's kind of a pain. There's some harder ones here. I mean, I think these are kind of the easier ones, and then those are a little tougher. But you can do this to any kind of function. You can do it to a sine function. That's tricky, though, to do it to a sine function.
I don't think we've done that.
I know, we have. It turns out, if you have a sine function, if f of x is your sine function, now I'm cheating. Now I've just time traveled to next week. You ready? Now I'm up ahead next week. The derivative is cosine x.
Now give it a slope of.
It's not fair to time travel on you guys, is it? I mean, I don't know. What am I saying? I'm saying the rest of your life, you memorize this. A lot of these things. The derivative of sine is cosine. The derivative of sine x is cosine x. The slope of the sine function is a formula. The formula for the slope of the sine function is the cosine function. It tells me the slope of that one. Right. It's the derivative of that one. How do you prove it? How do you prove that this is the derivative? You have to go back to what a derivative is. What is a derivative? It's this long mess. I mean, so to prove that he's a derivative, you have to do this. I got to do the limit as delta x goes to 0. I got to do sine of x plus delta x minus sine of x all over delta x. If I crank this out and do this, this is the derivative. This is the derivative of a function. And in the end, what's the answer? Cosine x. Somehow. It's tricky. This is a tricky one. It's not as fun as this algebra is a little funner. Now that we're here, might as well try to do it.
Not hard.
Let's see, how do we do it? There's a special identity. This is weird though. From trig, there's a special identity for the sum of two angles. I mean, it's not that obscure, but it's rather obscure. You could look it up. It's the sum of two angles. It's the sine of x, the cosine of delta x, minus the sine of delta x, cosine of x, something like that.
Yeah.
I might have just did it wrong though. Can anybody check on me? How do you check on me? You can look it up. The front of this book has some trig identities. Let me see. There's this front cover here that has, and on the back page there's all kinds of trig stuff. This is the sum of two angles, like u plus v down there at the bottom. Sine u cosine v plus cosine u sine v.
So,
I kind of did it right, but it was supposed to be plus. This is supposed to be plus. If that's plus, this is plus.
okay.
So what did I do? I used an identity right here. Now what? Oh my God.
You got it.
Here's what we do next. I'm gonna do a little rearranging here. Watch this. I'm gonna rearrange these two terms. So I'm gonna write sine delta x cosine x all over delta x. That's plus this sine x cosine delta x minus sine x all over delta x. Now wait a minute. I did a few moves at once. Do you trust me or do you need some explanations? I mean, you know what? It is all over one common denominator, delta x. It is. But I wanted to separate it into two separate denominators, delta x, like I did, which is okay. When you add these, I could write one long fraction bar with delta, or I can separate it like that. This limit was a little theorem. This was a little theorem.
Oh, I see.
The limit of sine delta x over delta x, and then it's multiplied by this cosine x, but as delta x goes to 0, this goes to 1.
Yeah.
That was a special theorem from chapter 2, so that goes to 1. Hold on a second. This other guy, I'm going to factor out a sine x, and I'll have cosine delta x minus 1 all over delta x. You know what? I think this was a theorem. It was a little more obscure theorem. And you think it was 1 minus? Well, I can make it 1 minus if I factor out a negative sign. Here, I'll factor out a negative sign, and I'll change it to this. That's legal, dude. I swear to God, it's legal.
Why was...
I factored out a negative sign, but this is a theorem. And this was a theorem, and I didn't use it as much. Y'all didn't use it as much, maybe, but this says it's 0. So that's 0, that's a 1. What's the answer? Cosine x. We just proved it. We just proved the derivative. This is the derivative. This is the answer to this limit. When you do this limit, he goes to 1, he goes to 0 from the special limits of chapter 2, and we get this answer. like I said, I might be a little bit into next week. But I'm not really, in the sense that I'm doing this. This is 3.1, and that's this week. We need to do 3.1 this week. So that's a little tough, that's kind of a tougher one.
I have a question.
Yes.
When you're doing that factoring on the second one, that sin x cosine delta x
Yeah.
minus sin x, you took out a
Oh.
negative?
Well, hang on. Then it is negative, right? Hang on, was this plus? This was a plus.
That was,
So it was plus.
so,
When I factor out a sine x, I'm left with cosine delta x minus 1.
okay.
And we wanted the theorem had those backwards. I think you're right. You said that, and I think
Yeah, so now when you
So-
take out, you'll
so-
put a negative.
So when I take out a negative sign,
That'd
yeah.
be a minus there, but it doesn't matter because it's gonna be multiplied.
Well, you're right. It doesn't matter too much. Now when I take out a minus sign,
Okay.
this will be a minus sign.
That's what I was
It
confused.
doesn't matter too much because that dude is headed towards
Correct.
0. But I think now we're more correct. You're right.
Yeah. I got it.
We were less correct, and now we're more
But
correct.
it doesn't matter.
Can you
Yes.
kind of repeat how you get the sin x 1 minus cosine x? I don't know how to
Right. So I factored out a sine x,
Gotcha.
and I'm left with cosine delta x minus 1.
Okay.
But then I remember that the theorem has those backwards.
Right.
So if I factor out a negative sign, that'll be a plus 1, and that'll be a negative. If I factor out a negative sign, he'll be negative and he'll be positive. So if I factor out a negative sign, he'll be negative and he'll be positive. So I just swapped the way I wrote them. He was negative, he was positive, and I just reordered them. It's the same thing. Okay. All right, I'll tell you what. Let's quit this a little bit. We may want to revisit some of this Wednesday if you guys work on a little 3.1 homework. Maybe you have some questions for me. What about 2.4 or 2.5 homework? You got any questions in there? I got one. I got one. In 2.4, there's this 68. It looks a little weird, 68. It's a function. 2e to the ax minus 2. It's a piecewise function. 2e to the ax minus 2. X is less than 4. And then it's ln less than or equal to 4. Less than or equal to ln x minus 3 plus x squared. ln x minus 3 plus x squared. So that's equal to, this is greater than 4. So there it is. It's a piecewise function. What's funny is it's got this little constant a. It's got this unknown a in it. And what the question is up at the beginning is find a, find that number a, so that this function, f of x, is continuous. So they want me to find the right number a that would make this continuous. You know, that continuity subject wasn't all that complicated, but the continuity concept did have that as three-step definition. But what, and it really is a three-step definition. You do need all 3 steps. But what do you think the most important step was? What was the big theme you got out of last week?
Number 2 to the left.
Kind of number 2. I mean, I needed the left and right needed to line up, which was kind of that the limit from the left and the limit from the right had to equal each other. I mean, that was number 2 of my definition, right? Right. So to be continuous, I feel like the left and right need to match up. Well, by the way, they want this to be continuous. where do you think I should try to, I mean, at which x am I worried about?
4.
Thank you, at 4. I'm worried about 4. Exactly. That's what you, on these piecewise functions, this is where it breaks. And maybe if we wanted the y values to line up. So what I want is the limit as you approach 4 from the left to equal the limit as you approach 4 from the right. And if you remember, that basically meant plug a 4 into there and plug a 4 into there and make sure they're equal to each other. It really was. That's what it was. But I'm a little worried about saying plug a 4 into there. I mean, technically I am plugging a 4 into there, but I'm doing a limit as x approaches 4 from the right. And I'm doing a limit as x approaches 4 from the left. That's what I'm doing. And I want them to be equal. I feel like if I can get those limits to be equal, then it's going to be continuous. So, I want to do that. I want to do the limit as x approaches 4 from the left of this function, and I want to set it equal to the limit as x approaches 4 from the right of this function. So here we go. On the left of 4, you're up here. You plug in a 4 for x. You plug in a 4 for x, and what do you get? 2e to the 4a.
4.
Well,
Oh,
you're plugging in a 4 for
4a,
x.
right.
You don't know a. A is the unknown.
4.
4a minus 2. You just plugged in a 4 on the left, and that's what you got. And you got this unknown a that you're going to try to find. What about on the right? You plug in a 4 on the right, and you get the ln of 4 minus 3. Well, that's the ln of 1. The ln of 1 happens to be 0. Your calculator would help you with that. But that's a 1, and the ln of 1 is 0. You plug in a 4 there, and you get 16. So what's the limit on the right? 16. So you do the limit from the left, the limit from the right, you set them equal to each other, and you try to solve for a. You try to find the a that makes it continuous. I like these little questions. They're not that hard. I broke it down pretty nice for you, but it's interesting, I think. You can find the a that will make these things line up. I would, you got to solve for a. I would add the 2 to the other side, right?
Yep.
I mean, now it's an algebra problem. 2e to the 4a, what do I do? Add 2 equals 18. Divide by 2?
Yeah.
So e to the 4a equals 9. ln both sides? So 4a equals the ln of 9. Divide by 4. A is the ln of 9 divided by 4. Woohoo! That was my number when I played high school checkers.